Hi, I'm here to show you the large rocket here that's 3D printed that I'm going to be using for my L3 certification. It's 2.5 meters tall, although you can't see the top because it's too big to fit in the frame. And this technology that I used to build this rocket was used to build these rockets as well as many others. These are the rockets I used for my L1 certification, was the one that resembles this one here. And my L2 certification, this one here that I got my L2 certification with. So I wanted to first present these two rockets here real quickly because the technology used in here and many of the parts and much of the flight heritage that's in this rocket was already validated with these smaller rockets. So I'll start off with this one here. So this one here, what's interesting about it is it's only made up of, essentially the rocket itself is only 3 parts. You've got the nose cone and the middle part, which is a body tube that screws in to the tail section, and then the tail section's here. So it's only 3 parts. There's no painting, there's no glue, there's no drilling of holes, and everything screws together. Even the motor screws in and out. So this is a single grain 52 millimeter motor. But I can also, there we go. Now the threads are printed inside the body tube. This liner here just slips in and can come out and be replaced if need be. Cardboard liner that insulates the hot motor housing from the rocket itself. So this is designed for a 1515 rail. All these are just 3D printed, all in one part here for the rail. And the motor, as I said, is a 54 millimeter single grain, but I can also put a 2 grain 54 millimeter in here. So it would be like a J size motor. This is like an I size motor. But I can also, with this adapter here, put in a 38 millimeter motor in here. And this is all 3D printed as well. So in here is a module that I can undo with this 3D printed wrench. Let's go in here. And I can unscrew what I call the ejection cartridge. So the ejection cartridge is 3D printed cartridge that you can see here with an RCC2 plus board in here, altimeter that fires the ejection charge right here. This part just screws in. As you saw, I unscrewed it, and it also has the attachment for the shock cord. So the nose cone also has a module. I can attach the shock cord of the nose here. And this module is the tracking module. It unscrews like so. And I can have, so I have a T3 tracking telemetry transmitter with a GPS on it. There's also an altimeter here, so it's a redundant altimeter. This exact module fits into the nose cone of this rocket here. So that's all heritage. This has all been flown and it works. Okay, I don't have a lot to say about the L2 rocket I use other than it's a 4-inch diameter rocket, the same as the big one here. And all this was successfully flown as well. So what I'm going to do now is I'm going to make room for this on this table to put all the parts of this rocket. I'm going to take it all apart so we can get into seeing what's inside of these. Okay, so now I've dismantled into its 3 main parts plus the motor of the 2.5 meter tall 35-pound rocket I'll be using for L3 certification. This motor here is a 4-grained 75mm motor. I currently have loaded it with grains of my own fabrication, and so it's actually an L-size motor, so I'm allowed to do that since I'm level 2 right now. And I'll be doing a test launch. This is the drawbar that holds into the fin section. So the way that works, the motor goes in here like so, and then the drawbar goes down inside and screws into the motor forward mounting part. And now it doesn't come out. Okay, so that's classic how that works. Everything here is, of course, 3D printed. These are the 1515 launch lugs printed onto the rocket. And the fins are a classic design with swept angles on the forward and trailing edges and so forth. By the way, I said 1515 for the smaller rockets. They actually have a 1010 rail lugs. So that's the tail section. This is the section that contains the drogue chute, so it normally mates onto here. And this is the electronics bay. So all of the attachments that have to detach, like here, have holes. You can see them here. These are all printed into the rocket. These are the holes that have actual metal inserts, and these are for the 4040 screws, nylon screws. They're used as pins to hold everything together. This part is held to the electronics bay with 1/4-20 stainless steel bolts that go through these holes. That holds it all together, and ditto on the other side. The electronics bay is a single part. It's 3D printed. There's, I believe, 56 holes, all 3D printed all over the place. These holes here have inserts. These inserts are heat formed and screwed into the plastic PLA that I'm using. And then the screws go through the body and into the threaded inserts. And that's how all this gets held together. The drogue chute and the main chute, which is over in this part of the rocket, are all ejected through a dual redundancy system. So there's 2 altimeters. There's one over here and one over here. Each altimeter has its own battery, a 3.7 volt LiPo lithium polymer battery, which is on the underside. All this is held together in a carriage, 3D printed carriage that holds the board, holds the on-off switch. This is one of the screw type that you put into your screwdriver and you turn it and it turns it on and off. And the lithium polymer battery is held to the carriage by a second 3D printed part on the underside, so it's underneath this board here. So everything is totally redundant, so each board can fire a drogue chute charge and the main chute charge, and then the other board fires the drogue chute charge 1 second later and the main chute charge at a slightly lower altitude. So you have dual redundancy. Completely, totally independent charges, totally independent cables, totally independent electronics, totally independent batteries. Okay, on each side there's a bolt that goes through this. This is just one solid, mostly solid piece of plastic. This bolt here goes through there, and it has this is a 5/16" stainless steel bolt, and it has 2 eye bolts on it to hook up the recovery systems to, and that goes through here. So throughout the recovery system and its 1-inch tubular nylon recovery cords are all held to these eye bolts, like this one here, this one here, this one here, and then there's one in the nose cone. So there's a continuous either metal from from the eye bolts, like this rod that's going through here, the rod that's going down to the motor. So from the motor through to this eye bolt, through some nylon, 1-inch tubular nylon, and into here, another bolt that's going through here, nylon, and then it goes into bolt into here. So there's either nylon tubing or stainless steel from motor to nose cone throughout the whole thing. Okay, so we've looked at this. Now the main section is just bigger than the drogue section, because the drogue chute is a 1 meter diameter parachute. This main section has a 3 meter or 9 foot diameter parachute in it, and the nose is also held in with 440 nylon screw shear pins, and you can see the shear pin holes printed here, and then these are reinforced with an insert, a metal insert. Okay, now this has exactly the same module that we saw in the smaller rockets for the tracking telemetry transmitter. So it unscrews and comes out. Now this one I've removed the altimeter, which would normally fit in here, because they're in the eBay here. So that it just has just the telemetry transmitter and a 3.7 volt 750 milliamp hour lithium polymer battery that powers the telemetry transmitter. So the nose cone is a 1/2 parabolic curved formed nose cone. It's all 3D printed. This curve is exactly, precisely defined by the mathematical equation for a half parabol curve. If you want to do a von Karman curve, you can also plug that into the CAD program that I use to draw all these. And to do a von Karman nose cone curve, I selected the 1/2 cosine because I like it better because it has more of a rounded nose, so there's less potential of damage on the nose. And so that, and then plus the half parabolic nose cone actually works better at subsonic and transonic speeds, which is what this is going to be flying at. Even with an in motor, it'll maybe break the sound barrier. The other ones, especially the smaller one, go faster than the speed of sound when equipped with the right motor. Those have all survived supersonic speeds, all 3D printed. So the technology has been pretty much proven in the smaller rockets. So I'm pretty confident that this will successfully fly, at least structurally. The structural part of the rocket should be strong enough. I mean, this thing's like built like a tank. I mean, this is all 5 millimeter thick, what's called PLA plus or tough PLA. So it's a very strong 3D printing material. I mean, this thing is. I mean, this type of PLA is about equivalent to plywood. So that you can imagine, this is essentially 5 millimeters of plywood. It's extremely strong because of its thickness. It's heavy. It's things built like a tank, but you know, I don't have a problem with weight in this rocket with a big motor. So so that's why I built it so heavy and so strong. I mean, these fins are just like, I mean, this is like 5 millimeter plywood. I mean, this thing, you know, it's strong. So, and of course, this is all one part. There's no glue, there's no seams, there's no things that can break apart at the seams because it's all one part. So that's it. I'll be launching this in a few days with the L-size motor to also prove the design and prove to the world that this actually works. And then later on, probably a month from now, the next launch site, I'll launch it with an M-class motor for the actual certification. Okay. This is the electronics bay. You can see here where one of the altimeters goes in this section here. These are the ejection charge ports. There's a metal liner that goes in here that is for the ejection charge. This is for the eye bolts. There's a 3/8 inch stainless steel rod that goes through the whole thing with 2 eye bolts screwed on each end. And you can see that this hole right here is to turn on the altimeter. On the other side, there's another alcove here for the second altimeter. So there's full dual redundancy with its on-off button hole here. And then you can see on this side here, this happens to be the main chute side. And then this is the drogue chute side here. So for each of the drogue and main chutes, there's 2 ejection charges, each driven by the 2 altimeters. So you have dual redundancy everywhere. Underneath the altimeter that goes in the holes here, each altimeter has its own lithium polymer battery. The fin body is here. And this is all one piece with one of the rail guides here, and then the body tube that goes above it has the other 2 rail guides. So you can see that all the fins are profiled with V chamfers and large fillets. This is all very strong, and it's all flown before. The thickness of the tubing everywhere is 5 millimeters. This is one of the adapter tubes that goes on the end of a body tube and joins up to, this section would join up to the drogue. So there's a eye bolt here that goes through. This eye bolt is the one that goes all the way through into the motor itself. So the motor and eye bolt and this part are all attached together. This is the nose cone. So it's all one part, and you can see in this section here is where this is actually threaded normally when it's printed. So this is where the tracking telemeter screws into here. And this is an example of one of the body tubes, but there's actually like 3 of these total. This body tube has bolts for 1/4-20 stainless steel bolts that bolts this onto the E-bay. This is a pressurization equalization hole here, so it essentially allows air to go in and out the body tube as the rocket goes up and down. And this hole here and the one on the other side here are for the shear pins. And so this is an example of one of the 4 rings used for the motor mount. So this actually is the one that's on the end of the motor itself. So, and this is like 40 millimeters wide, so it's very wide. The other motor mount rings are either 40 millimeters or 20 millimeters wide, so they're very thick and very strong. And this is the actual cradle that's used to attach the altimeter into the E-bay. So the altimeter actually bolts on, screws on through these 2 spots here. And then this is where the on-off switch is located. This is a time-lapse video of the tail section being printed. The actual print took about 3 days just to make this one part. It's the part that took the most amount of time. It also took 1.5 reels of filament. And then this is the E-bay being printed. And you can see there's some infilling done, cubic infilling done in the inside. And this is the motor mount. It has 4 3D printed parts in plastic, plus a cardboard motor mount tube. And you can see some plywood that's glued on the rear to insulate it from the plastic. And on the upper end, there's also some plywood on the inside that you can. On June 12th, 2021 at Misfits in Nevada, this rocket was launched with a home-built L1118 motor in the 5120 casing, exactly the same one that I'm going to be using for the L3 certification. The rocket was recovered and all went well.